You think you know what a black hole is. You've seen the pictures, the movies, the documentaries with ominous music and swirling CGI. You imagine a black hole as some kind of cosmic drain, a hole in the universe, a place where things fall in and disappear forever. Maybe you picture it pulling on nearby stars like a vacuum cleaner, or maybe you imagine it as a tear in the fabric of space, a rip in reality that leads somewhere else, another dimension, a parallel universe, who knows? That's not what a black hole is. And until you throw away those images, every explanation you hear will confuse you more. Because you're trying to fit the real physics into a picture that doesn't match. You're trying to understand something genuinely strange using familiar ideas that don't apply. Let me show you what I mean. Start with the name, black hole. It sounds dramatic. It sounds like there's a hole somewhere, an actual gap in space that you could fall through. But there's no hole. There's no gap, there's no tear in anything. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape. That's it. That's the definition. It's not a portal. It's not a vacuum. It's just a place where the gravitational pull exceeds a certain threshold. But wait, that doesn't sound so mysterious, does it? Strong gravity. Big deal. The Earth has gravity. The Sun has stronger gravity. What's special about a black hole? Here's what's special. And this is where your intuition is going to fight you. You think of gravity as a force that pulls on things, like a string attached to objects tugging them toward a massive body. That's Newton's picture, and it works beautifully for most situations. It gets rockets to the moon, it predicts eclipses, it explains why apples fall. But Newton's picture is incomplete. It tells you how to calculate the pull, but it doesn't tell you what gravity actually is. Doesn't tell you how the Earth reaches across empty space and pulls on the apple. What's doing the pulling? What's in between? Newton himself admitted he didn't know. He said he wouldn't feign hypotheses. He gave us the math, but he left the mechanism as a mystery. Then Einstein came along and said something extraordinary. He said gravity isn't a force at all. Gravity is geometry. Gravity is the shape of space and time. Stop. Read that again. Gravity is the shape of space and time. That sounds like poetry. It sounds like something someone says to sound profound without actually explaining anything. But it's not poetry. It's a precise, testable statement about how the universe works. And once you understand it, black holes suddenly make sense. Here's the idea. You're used to thinking of space as a fixed stage, a big empty box where things happen. Objects move through space. Time ticks along uniformly in the background. Space is just there, unchanging, like the stage in a theater that doesn't care what play you're performing. That picture is wrong. Space is not a stage. Space is more like a fabric. It can bend, it can stretch, it can curve. And when mass is present, when you put something heavy into space, the space around that mass warps. Not the stuff in space, the space itself. This is hard to visualize because you live inside space. You can't step outside and look at it from above. But think of it this way. Imagine you're an ant living on a rubber sheet. You think the sheet is flat because everywhere you walk it feels flat locally. But if someone puts a bowling ball in the middle of the sheet curves. And now when you walk in a straight line, you don't go where you expect. Your path curves toward the bowling ball. Not because something is pulling you, but because the shortest path through the curved surface isn't a straight line anymore. That's what gravity does. Mass curves space-time. And objects moving through curved space-time follow curved paths. They look like they're being pulled, but really they're just following the geometry. They're taking the straightest possible path through a space that isn't flat. This is not a metaphor. This is measurable. We've measured time running slower near massive objects. We've measured light bending around the sun. We've detected gravitational waves, ripples in space-time itself traveling across the universe. The geometry of space is real. It's physical. It affects everything. Now, take this idea and push it to the extreme. What happens when you pack more and more mass into a smaller and smaller space? The curvature increases. The dip in the rubber sheet gets deeper. At some point, the curvature becomes so extreme that something remarkable happens. Imagine you're on that rubber sheet near a very massive object. You want to escape. You throw a ball upward, away from the mass. If the curvature is gentle, the ball goes up, slows down, comes back. That's just orbital mechanics. Nothing special. But what if the curvature is so steep that even if you throw the ball at the speed of light, the fastest possible speed, it can't escape. It curves back. It falls in. That's a black hole. The boundary where this happens is called the event horizon. It's not a physical surface. It's not a wall you can touch. It's a mathematical boundary. It's the point of no return. Inside the event horizon, the curvature is so extreme that all paths, even paths taken by light, lead inward. Let me be very precise here because this is where people get confused. The event horizon is not where the mass is. The mass has collapsed to an incredibly small region at the center, what we call the singularity. The event horizon is just the boundary around that region where escape becomes impossible. Outside the event horizon, space is curved, but you can still escape if you have enough velocity. Inside the event horizon, there's no velocity high enough. Every direction points toward the center. Time and space get so twisted that the inward direction becomes the future. You can no more avoid falling to the center than you can avoid moving into the future. That's what makes black holes strange. It's not that they suck things in. They don't actively pull any harder than any other object of the same mass would. If the sun suddenly collapsed into a black hole, same mass, just compressed, the Earth would keep orbiting exactly as it does now. No extra pulling, no vacuum cleaner effect. The gravitational field far from the black hole is exactly the same as it was before. What's strange is what happens when you get close. When you cross that boundary where the curvature becomes so extreme that the geometry of space-time itself conspires against escape. Now here's something that should really bother you. What happens to time near a black hole? You've heard that time slows down in strong gravitational fields. That's true. We've measured it. Clocks on mountaintops tick slightly faster than clocks at sea level. Clocks on GPS satellites tick faster than clocks on the ground. The difference is tiny, fractions of a second over years, but it's real. Near a black hole, this effect becomes enormous. Imagine you're far away watching a friend fall toward a black hole. What do you see? You see your friend falling, getting closer to the event horizon. But as they get closer, you see something strange. They slow down. Their clock, if you could see it, ticks slower and slower. The light coming from them gets redder and dimmer, stretched out by the gravity. From your perspective, your friend never actually crosses the event horizon. They just slow down, getting dimmer and redder, asymptotically approaching the boundary. In your time, it takes forever. But from your friend's perspective, nothing special happens at the horizon. They cross it in finite time. They might not even notice the moment they cross. Space looks normal locally. There's no wall, no barrier, no dramatic transition, just curved space-time that they're moving through. After they cross, they can't send a signal back to you. Light can't escape, but they're still there for a while. They continue falling toward the center, and eventually they encounter regions where the tidal forces become enormous. Different parts of their body experience such different gravitational pulls that they get stretched out, a rather gruesome process poetically called spaghettification. But here's the strange part. Both perspectives are correct. From your viewpoint, they take infinite time to cross. From their viewpoint, they cross in finite time. This isn't a paradox. It's a feature of how time works in curved space-time. There's no absolute time that everyone agrees on. Time itself is relative. This is genuinely weird. It's not a trick of perception. It's not an optical illusion. It's how the universe actually works. Now let me address the thing you really want to know. What's at the center? What happens at the singularity? Honest answer, we don't know. Our equations break down there. The curvature goes to infinity, density goes to infinity, temperature goes to infinity. All our mathematical tools, which work beautifully everywhere else, give us nonsense at that point. This is a signal that we're missing something. The theory of general relativity, Einstein's theory of gravity, is a classical theory. It doesn't include quantum mechanics. And at the singularity, where everything is compressed to infinitely small scales, quantum effects must become important. We need a theory that combines gravity and quantum mechanics. We don't have one that works fully. There are candidates, string theory, loop quantum gravity, others, but none of them has been tested. None of them gives us a clear, confirmed picture of what happens at the center of a black hole. So when people tell you black holes lead to other universes, or they're portals to different dimensions, or they create baby universes, those are speculations. They might be true. They might not. We don't have the physics yet to answer those questions. What we do have is the physics of the event horizon and everything outside it. That physics is well tested. We've observed black holes. We've seen stars orbiting invisible massive objects. We've detected gravitational waves from black holes merging. We've imaged the shadow of black holes against the glow of hot gas around them. The physics works. But the interior, the singularity, the deep questions about what happens to information that falls in, those are open. Those are at the frontier of physics. Let me tell you what bothers physicists most about black holes. It's not the singularity, it's information. In quantum mechanics, information is never destroyed. The evolution of a quantum system is reversible. In principle, if you knew everything about a system now, you could run the equations backward and figure out what happened in the past. Information is conserved. But black holes seem to swallow information and never give it back. Things fall in. The black hole grows. Eventually, through a process called Hawking radiation, the black hole evaporates. It slowly radiates energy and shrinks. But the radiation that comes out seems to carry no information about what fell in. It's thermal, random, featureless. So where did the information go? Is it destroyed? Is it somehow encoded in the radiation in a way we don't understand? Is it stored somewhere inside the black hole until the very end? This is the black hole information paradox. It's been debated for decades. There are proposed resolutions, but none is universally accepted. This is an active area of research. People are working on it right now. What I want you to take away from this is not the answers, it's the questions. And more importantly, it's the approach. When you ask about black holes, you have to be careful about what kind of question you're asking. Some questions have answers. How strong is the gravity at a certain distance? We can calculate that. How long does it take to fall to the horizon? We can calculate that. What does the curvature of space-time look like? We have equations for that. But some questions are disguised as scientific when they're really philosophical. What does the singularity really look like? What's it like to be inside? What happens to you after you cross the horizon? These questions might have answers, but we can't get them. No information comes out. We can't do experiments. We can only calculate what our theories predict, and our theories break down precisely where those questions become interesting. This is the frustrating part of physics. The universe has regions that are, in principle, inaccessible to us. Not just practically inaccessible, not just too far away or too small a measure, but fundamentally inaccessible, causally disconnected. Information can't reach us from there. Does that mean we should stop asking? No. It means we should be honest about what we know and what we're guessing. It means we should be careful about the difference between prediction and speculation. Let me come back to the basic picture, because I want to make sure it's clear. A black hole is not a hole, it's not a vacuum, it's not a tear in space. It's a region of space-time where the curvature is so extreme that escape is impossible. The boundary of that region is the event horizon. It's not a physical surface, it's a geometric boundary. Inside the horizon, the geometry is so warped that all directions point toward the center. Time and space swap roles in a certain sense. Moving forward in time means moving toward the singularity. You can't avoid the center any more than you can avoid tomorrow. At the center, our equations give infinity. That means our equations are wrong there. We need new physics. We don't have it yet. From outside, someone falling toward a black hole appears to slow down and never cross the horizon. From their own perspective, they cross in finite time and continue falling. Both perspectives are valid. Time is relative. Black holes don't suck. They don't pull harder than any other object of the same mass. What they do is curve space-time so severely that close enough, no path leads outward. And this brings me to the deepest point. Gravity is not a force in the way you learned in school. Gravity is geometry. Mass tells space how to curve, and curved space tells mass how to move. That's the essence of Einstein's picture. When you understand that, black holes stop being mysterious magical objects and start being natural consequences of geometry pushed to extremes. They're what happens when you curve space-time so much that it folds in on itself. They're the universe's way of showing you that space and time aren't the absolute fixed stage you thought they were. Space can bend, time can slow, geometry can become so extreme that it traps light itself. That's not a violation of nature. That's nature revealing how deep its rules really go. Now, You might find this unsatisfying. You want to know what it looks like inside. You want to know what happens at the singularity. You want a complete picture. I understand. But part of physics is accepting that some questions might not have answers we can access. Part of physics is being honest about the limits of knowledge. We know an enormous amount about black holes. We can calculate their properties. We can detect them. We can observe their effects. But there are boundaries, literal boundaries, event horizons, beyond which information cannot travel. The universe has secrets that it keeps. Does that mean we stop investigating? Of course not. We push the theory. We look for better theories. We search for subtle effects that might give us clues. We test the edges of what we know. But we don't pretend to know more than we do. We don't fill in the gaps with comfortable stories that have no evidence. We sit with the uncertainty and we keep asking questions. That's what science is, not a collection of final answers. A method for asking better questions. Black holes are one of the best questions the universe has ever asked us. What happens when geometry becomes extreme? What happens when space and time get so twisted that our usual intuitions collapse? What happens at the boundary of what can be known? We have partial answers. We have amazing mathematics. We have observations. And we have enormous, beautiful gaps where the physics gets hard and the questions get deeper. That's not a failure. That's an invitation. The universe is stranger than you thought. Not stranger in a fuzzy, mystical way. Stranger in a precise, measurable, mathematically rigorous way. Stranger in ways that force you to rebuild your intuitions from the ground up. Black holes aren't mysterious because we don't understand them. They're mysterious because we understand them enough to see how weird they really are. The mystery isn't ignorance. The mystery is the actual physics staring you in the face, telling you that space and time are not what you assumed. So the next time you see a picture of a black hole, that beautiful glowing ring around a dark center, remember what you're actually looking at. You're looking at geometry. You're looking at the shape of space-time curving so steeply that light itself orbits and falls. You're looking at the universe showing you its rules pushed to the edge. That's not a hole in space. That's space doing exactly what it does, bending, curving, responding to mass, but doing it so extremely that your everyday concepts break down. And that breaking down, that failure of intuition, that's not a flaw in your thinking. That's the signal that you're encountering something deep, something real, something that requires you to think harder, to look more carefully, to question what you thought you knew. Black holes are not what you think. They're better. They're one of the universe's finest examples of how reality exceeds imagination, how the actual physics is stranger than any science fiction, how the equations we scribble on paper describe phenomena so extreme that they bend the mind as thoroughly as they bend space. And we get to study them. We get to observe them. We get to ask what they mean. That's the privilege of being a curious species in a curious universe. The answers are incomplete. The questions are magnificent.